Oh, that's one pen sitting over there. Okay, so all nitrates are soluble, all of them. All sodium salts are soluble. But I know from looking at the list that barium sulfate is insoluble in water. So if I wanted to make barium sulfate, I would take some barium nitrate. This would be my delivery agent for barium into the solution, Ba2+, barium's in group 2. Because I know that all nitrates are soluble. Ba is a Ba2+, nitrate is NO3-. I need two individual minuses to match the two pluses. The delivery agent for my sodium should be for my sulfate should be either a sodium salt or a potassium salt or an ammonium salt, because all sodium salts are soluble, all potassium salts are soluble, and all ammonium salts are soluble. And by doing that, I make some sodium nitrate, which is not important to me because that's guaranteed to stay in solution because it's a sodium salt and it's a nitrate. But then I would make some barium sulfate, and barium sulfate is hideously insoluble in water, and this will precipitate. It will fall to the bottom of the flask, and then I can collect it, dry it, and do whatever it is that I want to do with it. Maybe use it as a pigment. It's used as the white. It's a very strong white color. Okay, so that's the balanced equation. Blow it up. Let's do the complete ionic. The complete ionic equation for this is guaranteed to be soluble because it's a nitrate. Therefore, those ions have split apart. So I've got some Ba2+ as an aqueous ion, and I have two nitrates as aqueous ions. Sodium sulfate, most sulfates are soluble, but all sodium salts are soluble. Sulfate was SO4 2-. You have to learn that list of polyatomic anions. And sodium's in group 1, so it's very easy to predict that that is a 1+. And then I have BaSO4, and this is not in solution, it's a solid. It has fallen out of the solution, it has precipitated. And then I have this, sodium nitrate, guaranteed to be soluble because it's a sodium salt, and also guaranteed to be soluble because it's a nitrate. So 2 Na+ and 2 NO3-. Okay. That's the complete ionic. That is everything that is swimming around inside the flask right now. Yeah.
Why don't you have to break apart the barium?
It's not in solution. Ionic compounds stay stuck together when they're in the solid form, but when they're in solution, ionic compounds dissociate and ionize. It's no longer in solution, it's a solid. Came out of solution. That's your precipitate right there. Okay, let's look at the net ionic equation. Break out the colored pen, and anything that appears on both sides of the equal sign, our arrow is the equal sign, goes away. Barium, Ba2 plus, on my left side. Is it on the right side? No, so I'm going to pass. Nitrate, NO3 minus. Okay, I have two of them on the left. No pens at all today. Two of them on the left, two of them on the right. They both go. Na pluses. Okay, I got two of them on the left, I got two of them on the right. And then sulfate on the left, but not on the right. So my net ionic equation is that some barium 2 plus ions meet some sulfate ions and cease to be in solution.
So with an ionic equation, you're just like putting in or writing down the things that it takes to get your main product or your precipitate. Okay.
And what do we call these?
Reactants.
Those are spectator ions. They're in solution, but they're just floating around. They play no role in the reaction at all, none. They're the delivery agents for the ions that actually do the reaction. Okay, so if I started to put numbers to this now, and I said, oh, I have this many grams of barium nitrate in this many milliliters of solution, all I'm really interested in deep down is this. How many ions of barium do I have? So the moles of barium, because there's one barium in barium nitrate, if I have a mole of barium nitrate, it means I have a mole of barium ions. And that's all I'm interested in. And a mole of sodium sulfate has a mole of sulfate ions. If I took into account the fact that there are two sodiums in sodium sulfate, I would be off on a wild goose chase because sodium does not play a role in this reaction. Does not play a role. It's a spectator ion. Okay. All right, let's write some numbers into this and see what we can get. So I'm going to have two solutions. Take some barium nitrate, and then I'm going to ask how much sulfate would I have to add to it to precipitate every last barium ion. And that happens when the number of moles of sulfate equals exactly the number of moles of barium. Okay? Now we can do this more than one way. I can do it a long way, it's more practice for you, where I tell you the mass of the barium that's then dissolved. You have to find the formula mass, and then you have to find the number of moles, and then you have to find the molarity. And then once that happens, we can find the volume. Let's do it that way. So I'm going to take 100 grams of barium nitrate and I'm going to dissolve, it says in, that's my first mistake, up to 125 milliliters. Water. I'll make it here. Okay. I have 100 grams of barium nitrate. I'm dissolving it up to 125 milliliters of aqueous solution. What volume of sodium sulfate solution, what volume of 0.150 molar sodium sulfate solution is needed to precipitate all the barium ions out of that solution? Okay. We're going to use these three equations. We've seen them before, and we're going to do them in this order. I'm going to turn the mass of barium nitrate that is in my question into a mole quantity by finding out what its formula mass is by reading the periodic table. I'm then going to turn that mole quantity into a molarity by taking the moles that I just calculated it and dividing it by the volume that's in the question. That volume currently is written as a milliliter, so I'm going to have to change it to liters. And then, M1V1 equals M2V2. I'm going at that point to know what the molarity of my solution is, I know what its volume is, I know what the molarity of the second solution is, but I don't know what its volume is. A. Find the moles of, I think it's really Ba2 plus. The moles of Ba2 plus is equal to the moles of barium nitrate. Okay, so moles of barium nitrate is equal to the mass of barium nitrate divided by the formula mass of barium nitrate. Okay, let's do it. 100. This question has 3 significant figures in it of precision right now. You can add more as you read the atomic masses off the periodic table. Just remember that you have to round this calculation up at the end. Don't round it too early, round it at the end. So barium, bottom of group 2. 137.32 has 2 numbers in its box on the periodic table. There's a 56 and a 137. 56 is the atomic number. Smaller of the two. What does the atomic number tell us? Number of protons. And the mass number tells us the number of protons and neutrons. Not currently using that information right now, but we will do again. So that's its grams per mole number. So that's going to be 137.3 plus. I'm going to have a nitrogen and 3 oxygens all twice. So that is 2 nitrogens and 6 oxygens. 2 times that 1 nitrogen and 2 times those 3 oxygens. My formula mass for nitrogen is right on 14. It's 14.006. So I'm going to let that be 14.01. And double it. And then I'm going to have 6 oxygens. And this is in grams per mole. Grams will cancel and the per mole will go up. Which is coincidentally the other day when I was looking at the dimensional analysis, the 1,000, which is our milliliters, needed to go up to the top because it was divided by a division. I was just staring right at it. It's Friday morning and I didn't want to do it. Oxygen. Oxygen is right at 16. It's 15.999. So it's better to round that up than it is. It doesn't matter. Leave it at 15.99, round it up to 16. Salts. There you go. We should break that down into 2 steps so that when you read it back, you can figure out what's going on. So tell me first what all of these numbers added together equals.
261.33688.
100 grams divided by 161 grams per mole. 200. It couldn't possibly be more. Which tells me that is
0.383.
okay. I have found out how many moles of barium nitrate I have made. That's this number. Because the number of moles of barium nitrate, there's 1 barium 2+ in that mole right there. Okay. Let's figure out. So now I can do a couple of. I can do this 2 slightly different ways. I now know how many moles. So I've got a beaker. And it's got some barium 2+ in it. And I need some sulfate in there as well. Okay? I know how many moles of barium are in my solution. So now what I've got to do is just make these numbers match so that the mole quantity of sulfate is the same. Small problem is that that came to me as a molarity. It came to me as moles per liter. Figure that out. All I have to do is this. Okay. Let's find the molarity of that barium nitrate. Molarity is and I took my 100 grams and I dissolved it up to 125. I didn't add 125 to it. That means this is a real molarity and not a molality. Don't have to worry about that. Okay, so here's my point 383. And I'm going to divide it by my volume. 1,000 milliliters is equal to 1 liter. So I need to convert my 125 milliliters into liters. So I have the 125, going to divide that 125 by the 1,000 milliliters that I need. Okay, so 1 milliliter is 1,000th of a liter. It's basically what we're getting at. But for every milliliter, I have 1,000th of a liter, and I have to convert my milliliters into liters. So if I have 125 milliliters, that's 125 thousandths of a liter. Okay, so just move the decimal point. If I divide by 10, the point goes here. If I divide by, oh wait, wrong way. If I divide by 10, the point goes here. Just put a 0 there. If I divide by 100, if I divide by 1,000, right? No, other way. From there. Yes, from here. That. Got 125. Divided by 10, I got 12 and a half. Divided by 100, I have 1.25. Divided by 1,000, I have 0.125. We get there eventually.
It's Monday morning.
It is, and I didn't have a weekend. I worked all weekend.
But it's a long weekend next weekend.
Yeah, I'm working that weekend as well. But I get the Monday.
And Tuesday.
I get the Monday off and the Tuesday off. I have another side gig you don't know about. Liters. Moles per liter. Okay, divide those two numbers.
3.064 moles per liter.
Whoop. It's what?
3.064 moles per liter. Oops.
Yep. That looks real.
Can you tell us about your second?
I refereed all weekend standing on my feet.
For what sport?
Fencing.
I did not expect that. I was thinking rugby. It was just soccer.
There was a big fencing tournament. Fortunately, it was in Austin this weekend, not Dallas like it's been the past 3 weekends out of the past month and a half. But yeah.
I saw someone wearing fencing stuff.
3 moles per liter is a lot. Solutions to be dilute and happy, they need to be less than that. We crammed an awful lot of mass into a equivalent size volume here. That's tempting, because there's going to be a point where hey, that solution is going to be saturated. It is, of course, a nitrate, so we can bank on that being pretty healthy. But that's a concentrated solution. Okay, part 3. Find the matching volume for sodium sulfate. Okay. 1 and 2. Scenario 1 is going to be barium nitrate. Scenario 2 is going to be the sodium sulfate. M1V1 equals M2V2. Okay, what do I know? I know the molarity of the barium nitrate. Done it, it's right there. I know the volume of the barium nitrate. It's in the question. Now it's in the question as a milliliter, and I just changed that milliliters into liters, which I absolutely had to do because that number needs to be a liter. That number right there needs to be a liter. This one doesn't. It just has to be the same unit as that one. So if you keep this as liters, as that 0.125 liters, then that answer is going to come out in liters. If you keep this one as milliliters, that one comes out as milliliters. Okay? M2. M2 is the molarity of the sodium sulfate. It's in the question. So I know that number, and that number, and that number, but I don't know the volume. Have to move this molarity across the equal sign, and when I do, it descends to be a denominator. So M1V1 over M2 is equal to V2. The molarities are going to cancel each other out, right? And the units for that volume are going to carry forward. So if you put that volume in liters, your answer comes out in liters. If you put that as milliliters, it comes out as milliliters. M1 from the question. Oh, where am I? Do I do it down here? Rewrite it. M1V1 over V2. No. Wasn't a V, it was an M. Equals V2. Okay, M1 is my 3.064 times volume 1. It's in the question. You could use the liter value that you just calculated, but hey, what if you made a mistake? What if you made a slight mistake? Leave the number that's in the question. Let's do this in milliliters. So that is in molarity. And I'm going to divide that by the 0.150 molarity, and my answer is going to come out in milliliters.
If we made a mistake in the second step, then our polarity would be wrong. Right?
Yes. Yes. If you made the same mistake, you might write the error, but yeah, no, probably not. That number times that number divided by that number, it's going to be a big number.
2,553.333.
Okay, so that's coming out as 3,000.
2,000.
2,000, still a big number. That's what happens when you put random numbers on the board. 2,000.
553.333, so start just round to
Yeah.
0.
So that is 2.5 liters. We really only allowed that first 3 digits right here. That is 2.55 liters. Because this is dilute. The sodium sulfate is dilute. You are going to need a lot more volume of that dilute solution. And it turned out that this one was concentrated. 3 molar is kind of a big number. 0.01 molar is kind of the number that you find in the lab when we mix chemicals together and just see if there's a color change. So I inadvertently made that number far too big. That should have been a smaller number. Okay? But the math still works. do it again. Acids and bases. The remaining, oh, there's something else in this chapter as well. We'll leave it for another day. Do acids and bases. I just remembered what else. I went through the book to see what else was in there, and then I remembered.
We're still a ways off from chapter 5, aren't we?
Half a lecture.
Okay.
Okay, the basis of all of that has its big payoff in the book in acid-base neutralizations. We've already seen them. Acid plus base makes salt plus water. These are double displacements. I'm going to write water plus salt. Where you take the front end of one of these and you switch it around. Oh, these are double displacements. A plus B makes AB plus CD makes AD and CB, and if I write this right, HCl plus NaOH makes HOH, there's your water, and NaCl. And of course, the HCl is a strong electrolyte because it's a strong acid, as is the sodium hydroxide, as is the sodium chloride, but HOH, H2O, is water, and that is a liquid. Okay.
If it has a hydroxide at the end, is it always going to be a base?
Yes. Except that one time when it's not.
I love chemistry.
That's boric acid. Well, we have those.
Why?
All right, let's write a question that contains two of the mathematical principles that we've already seen. Acid plus base makes salt plus water. So we're going to do an M1V1 equals M2V2 because these, you don't normally make these solutions yourself. They normally come from the stock room already made up at 0.100 moles per liter or 0.2 moles per liter or 1.0 or 1.5. They usually come already prepared. So let's dilute something first and then have it neutralize. Okay. All right, let's think. Going to have a stock solution of hydrochloric acid, and it is going to be this molarity, number yet to be determined. Take some milliliters of that stock solution. And dilute up to a new volume. How many milliliters of molarity sodium hydroxide how many milliliters of this molarity sodium hydroxide are required to neutralize the diluted HCl solution. Okay? So this is asking us to do two things in a row. The first thing we're going to do is take the solution that's given to us and then dilute it down to a new volume. Now we only have 3 equations. Which of those 3 equations are we going to use in the first step when we take a stock solution? We're going to throw those numbers in a second and change its volume. M1V1 equals M2V2. That's the equation we're going to use because we don't have a mass in the question. There's no mass in this question, so we don't fit. It doesn't fit. Molarity is moles per liter. Okay. That sounds familiar because the question says molarity in it multiple times, but not numbers of moles. It's all molarity and volume, so it's this one. Okay, what are we going to do for the second one, where it says, okay, now we know what the concentration of your solution is. How many milliliters of the sodium hydroxide are you going to use in order to make that reaction work? That one again. This one again. We're going to use that equation twice. One. Find the concentration of the diluted HCl. Okay, what's going to be the concentration of our stock solution?
0.5.
Good number. How many milliliters are you going to take out of that stock solution? And when it says stock solution, that means there's a great big jug of it in the stock room. So you can take however much you want out of it. 2 milliliters. And how much are we going to dilute it up to?
4.
No.
4 milliliters.
4. There's no glassware anywhere in this building that says here's the mark where that's where 4 milliliters is. So 10, 25, 50, 100, 125, 250.
25.
How many milliliters of what concentration sodium hydroxide are we going to need? I need a last number to go in here.
3.8.
Okay, we can do it. This question reads a lot more complicated than it is. It is M1V1 equals M2V2, followed by, oh, M1V1 equals M2V2. What? Yes. Find the concentration of the diluted HCl. So, on one side I'm going to have the stock, and on the other side I'm going to have the dilute. This will be M1V1 equals M2V2. What do I know? On the stock side, I know its concentration and I know its volume. I took the 2 milliliters. Trick question in the textbook would say a 450 milliliter stock solution. Now you're just tempted to use that number. They gave me a number, it's in the question, I have to use it. I've got a number in the question and I haven't used it yet. I've got to throw it in there somewhere. No, you don't. You don't need to use that at all. That's a red herring. That's the number that you've taken and you've moved forward. Once you take that out of the stock solution goes away. So I know its molarity and I know its volume. I also know the volume that it's been diluted up to. What I'm trying to find is its new concentration. This is just like we did a second ago. So M1V1 over V2, and as long as those volumes are in the same units, they better both be milliliters or they better both be liters. So long as they're in the same unit, it works out for you. So M1 is 0.500 times volume 1 divided by volume 2. If you write the units in, that's an indicator that you're on the right track. Don't just write the numbers. The numbers are meaningless without the units. Oh, that should be an easy number.
0.04.
Milliliters cancel and my moles per liter carry forward. Okay. I'm going to find the equivalent volume now of the sodium hydroxide. Okay. Just a reminder to ourselves that acid plus base makes salt plus water. And that at neutralization, the mole quantities of acid equals the mole quantities of base. Okay? And remember, oh, we can do it here. If molarity is moles times liters, then moles is molarity times liters. Oh, that's MV. So making M1V1 equal to M2V2 is matching the moles on the left to the moles on the right. It's matching the moles of acid to the moles of base. I write that down. That would be M acid times V acid equals M base times V base. Okay. What do I know from my question? I know that I have 2 milliliters. Nope, no I don't. I now have this volume. I have 25 milliliters of that concentration. That's the acid concentration. 0.04. Oh, do we have another, do we have digits? We don't, do we? And the volume is this. I'm going to leave that in milliliters. Equals concentration of the base. Is it in the question anywhere? Right there. Times the volume of the base, that's the thing that we're trying to find out. So the volume of the base equals 0.04 times 25 divided by 0.380. And that answer will be in milliliters. Who?
2.63.
2.63. Okay, so you've come up with an answer. Calculator's told you it's true. Is it? Does? So now what you've got to do is say to yourself, does it make sense? The number of moles of acid, M1V1, is going to be equal to the number of moles of base. So if they were both the same concentration, if I have 1 mole per liter of acid and 1 mole per liter of base, then I should expect to use a liter of this and a liter of that, or 100 milliliters of this and 100 milliliters of that. Because that volume is different to this volume, just look at the numbers in the question. The molarity of my acid is 0.04, and the molarity of my base is 0.4. Okay, I can live with that. It's the difference between 25 milliliters and 2.5 milliliters. It's a factor of 10. Checks out. I've never seen any of these numbers before, but my base is 10 times more concentrated approximately than my acid, and my volume of base is about 10 times smaller than my volume of acid. That checks out. So I'm comfortable with that, and I move on to the next question. All right, we're done. There is more to read in this chapter, just a tiny bit. It's about redox chemistry, where we do a reaction where one of the things gets oxidized and the other one gets reduced. We're going to hit that and then move on. Read ahead a little bit.
Is there any place we can get more practice problems or just the book?